Uh, okay. I'm Yue-Jiao Gong from the South China University of Technology. First, I'm I really apologize for postponing this talk for several months. But I'm excited that I finally have this opportunity to share our latest work along this direction of meta black box optimization. Thank you all for joining, and let's get start. Okay, this is the outline of my today's talk. First, as MetaBBO, I think it's a relatively new topic within the area. So I would like to first define some basic concepts related. And I would like also to explain why do we need this technique. Next, I will briefly introduce four major paradigms of MetaBBO, and then I will introduce several of our recent works by using meta-learning to manipulate the optimization algorithm to improve the performance. And finally, some concluding remarks. Okay, first, what is MetaBBO? If we ask ChatGPT this question, I think her answers may be very correct. It stands for Meta Black Box Optimization. It has a prefix, meta. It indicates that we usually involve some meta learning steps to learn something about the optimization process itself, but rather than just solving a single problem. So another term is BBO. I bet today's audience, may be very familiar with this concept. It refers to a specific optimization scenario that we cannot know the internal structure or some mathematical properties of our objective functions or constraints. So the optimization process is conducted based on only the observation of the input output. So the solutions and the objective evaluation values, this pair of the function. So then it briefly summarizes that MetaBBO aims to develop or adapt optimization strategies that can be effectively solve a variety of BBO problems. It's this area, I think it locates in the intersection of several areas such as deep learning, reinforcement learning, and evolutionary computation. So more formally, we think that MetaBBO can be defined as this bi-level framework. In the lower level, I think it's just like we usually do, what we previously do to solve a BBO problem, that there is a low-level optimizer. It generates and updates the solutions to the optimization problem, and we evaluate these solutions to return the objective values, and then the optimizer updates the solutions. But in MetaBBO, there is a meta-level controller here. It's engaged of designing the lower level optimizers, such as configure or even generate the low-level optimizer. So the learning objective is like the meta-level controller is developed to seek a kind of policy which is usually represented by a neural network, for example, parameterized by some parameters theta in order to maximize this j of theta, which is the meta objective here. So in this equation, this A is the low-level optimizer here, and it can have a broad concept, I think. It can be an optimization algorithm or an algorithm pool or some specific structure to create new algorithms. And F here, P here is the collection of problem instances, and we will sample, for example, a number of big N problem instances from this collection. And the meta objective is to maximize the performance gain for these problem distributions and over a certain number of optimization steps T. So pi, the policy pi works here. It receives some optimization state features to generate some design parameters or some other things, design choices to maximize this meta objective. So just now we have defined what is MetaBBO. So the next question is, why do we need this technique? Let us think about how do we solve a practical problem? Usually we will have these two steps. First is the algorithm design step, because there is no free lunch theory that we do not have any algorithm that can have dominant performance on all different kinds of problem. So usually a human expert would spend lots of time to analyze the problem and to design the algorithm, to test the algorithm or adapt the algorithm so as to improve the performance. Then after that, the computing system execute the algorithm and generates the solution. But previously, when we want to evaluate the performance of problem solving, we pay attention only to this component. For example, if we where we are writing a paper, we report the performance such as the execution cost and the learning, and the accuracy of our solution, etc. But we overlook the cost in this part, which is, however, very time consuming and labor intensive. So then the MetaBBO comes in handy. It helps us to automatically design the algorithms. It can design different algorithms for different problem instances so as to address the previous limitations of manual algorithm design, such as the label intensiveness, the limited generalization, and the suboptimal performance because of human design biases. So this is why do we need MetaBBO. Next, this page, I would like to briefly compare the MetaBBO with the area of NCO. The NCO, the neural combinatorial optimization, I think today's audience may be very interested in the area of NCO because there is a keyword combinatorial optimization in our task force. So NCO, generally speaking, it employs some neural networks, some policy to generate solutions to the combinatorial optimization problems. There are certain similarities of MetaBBO and NCO because they both fall under the category of learning to optimize, and they are these two areas are also relatively new and rapidly gaining popularity. But there are several distinctions, I think. first, MetaBBO, just now we have introduced that it focuses on black box optimization scenario, so we cannot exploit any detailed internal problem structure. And also, usually we use meta learning to emphasize the generalization of problem strategy. So the agent we learned need to applicable to a wide range of problem instances. For example, in our work, I will show it later. We will train a single agent that is applicable to, for example, to both the CEC benchmarks and also some realistic optimization problems, such as protein docking, hyperparameter tunings, etc. And for NCO, in contrast, so far, most of the NCO works, they deeply integrate the problem structure information into the model design, and they focus on specialized strategy tailored to specific combinatorial optimization problems, such as the TSP and different VIP variants, etc. So they often achieve very high performance by leveraging such problem-specific insights. So these are the distinctions between MetaBBO and NCO, I think. Okay, next I will start to describe the major paradigms of MetaBBO. We can use this meta-level controller in two aspects. I think first we can use it to manipulate on the algorithm flowchart, and the other direction is that we can directly adopt the controller to generate and update solutions. I would like to first introduce this second paradigm. For example, in this work, we can use a recurrent neural network. It receives some history solutions and the evaluations, and then the RNN use this RNN to generate new candidate solutions in each step. And then the loss function is constructed based on the evaluation values on these generated candidate solutions in order to train our network. And also recent years, because of the popularity of the large language models, there are also works such as this work, I think is Google's Opera. They follow a similar paradigm here, but they replace this RNN by LLM, which also receives the solution score pairs and to generate new solutions, and then evaluate this, and then go back to the LLM to further update the solutions. However, we think that so far there are still several limitations in these paradigms. This is because the complexity of solving the BBO problems, and there are vast different fitness landscapes of different optimization problems. So far, it's quite difficult to learn a neural network that can be generalized to different problems. So there are limitations in efficiency, scalability, generalizability, and interpretability. So in my talk today, I will focus on this branch of algorithm manipulation. First, algorithm selection, I think, is a long discussed area in the field of evolution computation for decades. So usually we construct an algorithm pool and collection of problem instances and train some thing like a neural network to train to select the optimal algorithm from the algorithm pool for each problem instance. So today I will focus on the algorithm configuration and algorithm generation. I will introduce the research works in our group along these two directions. First is algorithm configuration. I will start by this work named GLIT. I think it's the first attempt in our group to use a policy network to generate parameters for evolutionary computation algorithms. The general framework is like this. First, we have a collection of problem instances, and in our environment, there should be an evolutionary algorithm that engaged in optimizing different optimization problems. And then over a certain optimization period, we will extract some optimization status knowledge about the environment, and then we input this status to inform our agent to make decisions about the parameters tuning. And these parameters are related to the exploration and exploitation trade-off. And then the low-level optimizer receives this control and then continue its optimization. So the reward design is usually very straightforward, that we check how much gain we can performance gain we can obtain by executing this the algorithm with these parameters. So more specifically, we have designed this attention-based encoder-decoder architecture to process the raw features, such as which usually include the population distribution and the objective values and the distance between the individuals, etc. Then we treat each individual in the population as a token. Then we, after feature embedding, we have a fully informed encoder to let each individual pay attention to each other. And then finally, in the decoder, we will further let each individual pay attention to the EET embedding we learned, and then to generate its own parameters. So note that we jointly control all big N individuals' choices of M hyperparameters. So the total number of output heads of our network is N times M times 2, because we need to sample two parameters, the mean and standard deviation, to sample, because we perform continuous optimization. So we need to output these parameters in order to sample our concrete parameters. So the advantages of such an attention-based architecture, I think, is that first, GLIT is generalizable across different population sizes. And GLIT encourage the information sharing through the exploration and exploitation attention mechanism. Please wait me a moment. The second advantage Okay, thanks, Professor May. And the GLIT encourages. First is the GLIT is generable across different population sizes and problem dimensions. And second is we encourages the information sharing through this attention mechanism. So in the experiment, we use the CC benchmark with random rotations and shifts to argument our benchmark. And we perform in-distribution and out-of-distribution test. In-distribution test means that we train our and test our agent on the same group of functions, but different. For example, we can generate a large number of problems per function and use several for training and the rest for testing. For out-of-distribution test, first we can train and test our agent on different function classes, and we also try to train it on CC, but test it on another realistic problems. And just now you may notice that I did not specify the parameters or which parameters our GLIT control. This is because we tried to make our framework broadly applicable. And in the experiments, we tested on 3 algorithms. For the 2 PSO algorithms, we let M equals 1 and sample the coefficient C1 for each particle and leaving C2 as 4 minus C1. And for DE algorithms, we let our agent to control 3 parameters for each individual. And the results both shows we can observe certain performance improvements by the control of our agent. And also in the generalizability validation also shows our algorithm, our framework has a very good generalization in different cases in this out-of-distribution test. Okay, in our second work, this is one of our recent works. We make one step forward in the algorithm configuration. Briefly speaking, we propose a multitask framework. Just now in our GLIT, although it can be applied to both PSO and DE variants, but there is a limitation that we need to entirely retrain our neural network or our agent to let it capable of controlling the parameters for different algorithms. So we need to, although the framework is the same, but we need to frequently retraining it to fit different algorithms. So the basic motivation of this work named Config X is that we propose a multitask framework to address the limitation that current MetaBBO methods need custom network designs and frequent retraining to fit different backbone evolution algorithms. But however, we noticed that there are certain shared aspects of different evolutionary algorithms. So in this Config X framework, we try to learn a universal agent to fit different kinds of evolutionary algorithms. So more specifically, first we design a modularity system it's a kind of, you can consider it as a comprehensive algorithm design space that it leverages the hierarchical polymorphism to efficiently manage different algorithm sub-modules, such as the crossover, mutation, selection, and the PSO update rules. And we put all of this as component within a comprehensive algorithm space. And then, importantly, we propose a joint optimization task space. It's the task we encountered are no longer the problem instances themselves, but also a synergy of the algorithm space and the problem set. So then an optimization task contains a specific algorithm and a problem instance. So the meta objective becomes in this way. Here, K stands for the number of algorithms, and N stands for the number of problem instances. So we train our agent to maximize this kind of meta objectives in the joint optimization space. So after defining all this, we can design a transformer. We also need this self-attention network to meta-learn a universal configuration policy over this joint task space. So in the experiments, there are different problem spaces, including the synthetic problems and the real-world problems such as protein docking and the HPLB benchmarks. And the algorithm space, we consider the DE variant, the PSO, and the GA variant. So in the training, our training set is based on the joint space of D variants and the BBOB test suite. And we also perform in-distribution and out-of-distribution test. The in-distribution test, we focus on this. And for out-of-distribution tests, we try to test our trained agent here to the problem instances beyond this training set, and also the algorithm variants beyond this training set. So the results are briefly summarized here. First, the zero-shot performance of the pre-trained model are appealing. And then we can further fine-tuning our performance to the specific, for example, to the unseen problem optimization problems and the unseen algorithm structures, which can further improve the performance. And this figure shows that the red line the fine-tuning curve, and the blue line are the retraining, are the curves that we retrain our agent from scratch. So it can be observed that by fine-tuning our pre-trained model here, we can save 3 times and 2 times of the learning steps. Okay, this is the work we done, the studies we done for the studies we did for algorithm configuration. Next, I will introduce our work for algorithm generation. This symbol, first I would like to explain its motivation. This is the general flow chart of BBO. We have candidate solutions and some update rules to generate new solutions. And we have this loop until some terminal condition is met. So the in traditional BBO optimizer, we have human crafted rules as our update rule. And in traditional MetaBBO, for algorithm configuration, such as just the 2 words I just presented, we use some kind of neural network to configure these human crafted rules. And in the MetaBBO for candidate solution proposal, we adopt a neural network here to update, to generate new solutions to the problems. So in Symbol, we propose a novel framework that we use the neural network to generate the symbolic update rules in order to generate the new solutions in each iteration. So this update rule would be customized to each problem instances and at different optimization steps. So compared to the previous BBO for algorithm manipulation, the benefit is that we are more independent of the expert priors and offers greater flexibility and adaptability because we can control not only the parameters but also the operators here. And then compared with those methods for solution manipulation, we have improved efficiency and scalability and enhanced interpretability. Okay, more specifically, we built this recurrent neural network because it's our first attempt. Our network design is very simple. We simply adopt an LSTM-led network. And first, we built a basis symbol set. It has some operators and some operands. And then the LSTM network receives some features, such as the problem fitness landscape analysis features. And it auto-regressively generates tokens from our symbol set, and by a pre-order traversal on this sequence, we can generate a symbolic tree and interpret it into the update rule equation. Here, note that every time we sampled a constant C, here, we have two additional layers to output. We have two additional FF output nodes to generate the concrete values of this constant by generating its mantissa and exponent. So after that, the lower level update process, we use our fitness landscape analyzer to process our population, and then the SEG here is the symbolic equation generator. This is our network design here. It is engaged of generating the update equation in order to generate new solutions. And then the FLA features updates, and the SEG would generate new update equations, etc. So to training our network, we also model it as a Markov decision process. And let me see the time. Okay. We have three training modes. First is exploration learning. In this training mode, our reward design for pay attention only to the improvements of the evaluation values. This is our ultimate objective, but however, so far, due to the learning limitation of our RL masters, because of the design space in algorithm generation is very large, that is much larger than algorithm configuration, because we not only need to control the parameters, but also every operator in our update equation, the space is large. So, and the reward of training, this is usually very sparse, has sparse signal. So the performance, although it has some performance, but the symbol E, this version, still cannot defeat our human designed algorithm. So we try to guided learning our symbol from a teacher optimizer. Let the agent try to mimic the behavior of a teacher optimizer. And also in our final version, the symbol S, it performs synergized learning of this above two reward. So in the experiment, I will briefly introduce that we also perform in-distribution test and out-of-distribution test, HPLB and protein docking. And it shows that our symbol, especially the symbol S, exhibits very promising performance. And just now in these experiments, we use MetaBBO, which is one of the winners of the CEC 2021 computation, as our teacher optimizer. We also tried to test our framework on the other teacher optimizers such as DE, PSO, and CMA-ES, and on different test suite. And all the results show that by our design, the symbol S can surpasses its teacher optimizer. Okay. The last work I would like to show today is LaMoCo. It's you know that large language models are very popular nowadays, and we also want to try to use this technique for to solve optimization problems. And different from the previous, there are a certain number of works using LLM for optimization, but usually they follows a solution to solution paradigms, that they use LLM to receive solutions and to output solutions. And our solution is a novel code-to-code framework. It receives the optimization problem descriptions in LaTeX or Python format, and then we instruction tuned some of the LLMs to generate the optimization code. So we construct instruction set and specifically design a two-stage fine-tuning process to fine-tune this LLM. So, but briefly speaking, I think compared with those solution-to-solution LLM frameworks, our work provides the benefits such as the single round code generation, because these frameworks, they need multiple rounds of conversations. There are how many iterations required to solve the problem. So we need how many numbers of conversations with the LLM. So in this framework, one benefit is that we need only a single conversation to generate the code. Second is that because LLM are very sensitive to the prompts, so our solution is that we just provide it with the code distribution, which can be either LaTeX or Python, and reducing these prompt design efforts. So these are the results in distribution test and out of distribution test. And we compare our methods with the Google's Opera and LMEA, which are solution-to-solution framework that are published recently that use LLM for optimization. And we also compare our LaMoCo with we directly prompt this famous code LLM to generate the code. The result, both of the result, the in distribution and out of distribution result, shows there are certain effectiveness of our instruction tuning LaMoCo. I think that would be almost the end of my talk. I introduced MetaBBO. It helps us to enhance the algorithm design efficiency and reduces the reliance on experts and improves the generalization of optimization algorithms. And our work has progressed from using expert crafted rules with automatic parameter tuning to developing complete update formulas. And the future directions include fully end-to-end automation, because so far most of the works along this direction still use handcrafted problem features, and we can adopt more advanced models and to solve more complex or even mixture collection of tasks. And also we need to validate MetaBBO in more practical scenarios. There are two additional resources I would like to share with you. First is MetaBox. It's a benchmark platform to develop MetaBBO with reinforcement learning. This is an open source platform. We provide algorithm developed templates and some test suits and some baseline libraries for you to compare your algorithms. So if you are interested in this area, we welcome you to use our framework. And the second one is that we have finished a survey paper to this area. We categorize MetaBBO for these four tasks I introduced today: algorithm selection, configuration, solution manipulation, and algorithm generation. We also summarize different learning paradigms behind MetaBBO, including this reinforcement learning, neural evolution, supervised learning, and in-context learning with large language models. And we also provide some practical guides, such as we perform a detailed benchmarking by using the MetaBox here. And then we summarize some key design strategies in this area. So if you are interested, we also welcome you to read our survey paper. Okay, that is the end of my presentation today. I would like to introduce two of my PhD students, Zeyuan Ma and Hongshu Guo. Because they are my PhD students, then they spend lots of effort in this MetaBBO area. Most of the work I talked today, the concrete works are done by these two PhD students. And we also have a team page along this direction. All of our papers and codes are released on this GitHub page, and we welcome you to use them. And thank you once again for joining this talk, and I'm happy to answer if there are any questions. Thank you.